Today I wanted to do a video about another one of the crazy ideas in physics. It's one of my pet peeves. The black hole information paradox hoax. And this is an idea that was born from the wavy guys, the quantum mechanics guys who think that waves can exist without a medium, that you can have a waterway without water. And you can store information without a medium. And then you can store it indefinitely without a medium. And so it's just a crazy idea all around. And I'll just step through some of the problems. Number one, if you have a paradox, your theory is invalid. Just like if nature violates your law is wrong. So, right there, we know there's a huge problem. And there's problems on multiple fronts. Information conservation theory is invalid. First, particles don't carry information. Every electron, proton, or neutron is the same as every other electron, proton, or neutron. Except they can change spin. So you can possibly transmit limited information through spin entanglement, which is something people are playing with. Then we have quantum jumps. If you have an electron and an electron-positron quantum fluctuation can come along, positron annihilates with the electron, produces a new electron that was the quantum one, and the electron's gone. The electron's gone and your particle jumps. And you don't even know exactly where it was, and you don't know exactly what its velocity and momentum were. It still has the same state, and if it's in an atom, it stays in the same orbital usually, or it could jump orbital when that happens. But we can't store information in particles that are constantly changing, and by constantly, billions of times a second. All of our electrons and protons and neutrons are being constantly replaced. So wave functions are not physical particles, which is even worse. So now you don't have the particles that can't store the information in waves that can't store information. Instead, the information is stored in the quantum field. The quantum field has a history of angular momentum and momentum, and it has history of the rotation of objects. It has history of waves that have passed through it and waves that are passing through it. It has history, although no one's recording the history. The quantum information, though, is not destroyed in a black hole. Not any more than it's destroyed outside the black hole. The black hole isn't special. Yeah, it will destroy something that particles are made of without destroying the individual particles. And the quantum field around it will stay around it. And the quantum field is replaced continuously. Every single quantum fluctuation exists for a short period of time. And so whatever information was in that one quantum fluctuation gets replaced when the quantum fluctuations get replaced. Now the quantum fluctuations have to conserve momentum and angular momentum and the energy in waves and such. So waves can propagate, but you're still not, you don't have a fixed particulate memory. surface on which you're saving information. And then the other main part of the theory is the Hawking radiation theory is wrong. Virtual photons don't exist, number one. In order for virtual photons to exist, that means two photons. If you have two photons, you have too much energy. You have greater than 1/2 h nu, or 1/2 hf. 1/2 times Planck's constant times the frequency. That's the energy of quantum fluctuation. If you have two photons, you have too much, so they're not quantum fluctuations. You only get a quantum fluctuation if you have a single electron-positron pair, which is equivalent to 1/2 of a wavelength of one photon. So you can think of a photon being made of a series of electron-positron pairs, quantum fluctuations. And these quantum fluctuations are rotating alternately each half wavelength. And it produces a rotating electric and magnetic field as they go. But you can't get a rotating electric magnetic field without a rotating dipole being there. And if there wasn't a dipole there already, the quantum field would induce one into existence. So it's these electron-positrons that you have to consider, or proton-antiproton pair, but we have to consider what they do at the event horizon of a black hole. But importantly, they can't escape the event horizon. These are particles with mass. They can't travel at the speed of light. So once they're at the event horizon, they're stuck. They're going to stay there because the clock rate goes to 0. So they're stuck at the event horizon indefinitely. And once one manages to drift across the event horizon very slowly, the other one is going to follow it almost certainly. We may have, in very, very rare cases, two quantum fluctuations that occur side by side, where we have an electron-positron and positron-electron, and they cross, half of them cross the event horizon. There is a possibility that electron and positron can cross-annihilate from the two pairs and form a photon, and this photon might escape. I did a little drawing here. That's the only way you're going to get a photon to escape, is if you get an electron-positron annihilation at the event horizon, and you get a photon that just manages to escape. But it's going to take forever, and it's going to be redshifted almost to infinity, so almost to 0 energy. When we talk about Hawking radiation, we have to worry about the timescales. Anything that crosses the event horizon takes forever. Instead of talking about a Big Bang type timescale of 14 billion years, you're talking about tens of thousands of billions of years, or billions of years, because of the slowing of the clock rates of the event horizons. So Hawking radiation doesn't happen. So the idea of a black hole radiating away in any time frame that we would observe is nonsense. It's too slow of a process for it to occur. And the information can't be stored anywhere physically real anyway. We ultimately have the problem of you can't put an explosion back together. If we tried to put a bomb back together atom by atom that occurred in World War I, we couldn't do it. Because the information is not stored anyplace. It's not even available in the quantum field. There's no way to get to it. It's like shuffling the deck of cards 100 times and try to figure out what was the order 100 times ago. Well, if you could record the information for every shuffle, you could recreate what it was. But if you don't have that information, you can't. If you don't have the information what happened during each and every shuffle, you can't create the exact order. And so that information is lost. There's no physical place to store it. And that's why the conservation of information theory is wrong, because the physicists didn't think through the problem. Where's the information stored? They just thought they could pull it out of their ass and say they have a conservation theory. Anyway, I hope you enjoyed the video, and if you do, please like, share, and subscribe. And if you want to support my research, I'm an independent retired researcher, and by buying one of my books you can help me in my retirement, and so I appreciate that. Thanks for watching.